We're going to look at chapter 10 today. So chapter 10 is a chapter that goes over alkyl halides. So we're going to look at some different ways to prepare alkyl halides, and we can look at some reactions that alkyl halides undergo. And that'll carry on into chapter 11 as well. So the first thing we'll look at is some different ways to prepare alkyl halides. One way is from alkenes. So these are just the same reactions that we saw when we went over the alkene chapter. So we saw you could add HBr, and that's a way to add bromine. Markovnikov addition, so adds the most substituted position. Goes to a carbocation intermediate, so the bromine can attach from either side. And so you get a racemic mixture. Well, if you did that reaction in the presence of peroxides, what would be the difference? Goes to the least substituted instead. So here, this carbon is attached to 2, this one 1, so this is the least substituted. In that case, I do not have a chiral center, so no racemic mixture there. And then we also looked at a method that added 2 bromines. The most common solvent for this was like this carbon tetrachloride. Now, when you do have chiral centers, you do get the racemic mixture. This one was Markovnikov addition. This was anti-Markovnikov addition. This one, it formed that bromonium ion intermediate. And so we see that the bromines add to opposite sides. So we call that anti-addition. Now, another method that we touched on just briefly was halogenation of alkanes. And so this was alkenes here. You can also halogenate an alkane, so without the double bond. So in this reaction, chlorine or bromine can replace any hydrogen in the alkane in the presence of light. The reaction takes place through a radical mechanism. The radical mechanism, you have three different steps. You have initiation. So let's look at chlorination in this case. So I have chlorine in my solution. So I hit that with UV light. Chlorine splits apart into radicals with the UV light. I get 2 chloride radicals. Then I have my propagation step. And so I'm just using the simplest alkane here, methane. But if you have a larger alkane, this can take place with any hydrogen on your molecule. So that chloride radical takes off a hydrogen and it creates an alkyl radical. The alkyl radical can then react with more chlorine to create your alkyl halide plus another chloride radical. And so that chloride radical then could react with more methane. The process just repeats. Okay. But it can do that with any hydrogen in your molecule until you reach a termination step. In termination, it was two radicals come together. So I have a few different radicals here. I have this methyl radical. And I have chloride radical solution. So if they came together, make your alkyl halide. But the two methyl radicals could also combine with one another. Or your two chloride radicals could also combine with one another. There's various termination steps there. But overall, the reaction that you would see written would be CH4, Cl2, I put heat here. It should be UV light. Okay. So chlorine, UV light. The chlorine replaces one of the hydrogens. And that's how you'd see the equation written out. This reaction is actually a poor method of producing alkyl halides because a mixture of products results. Let's write that out again. So I say I get CH3Cl. So as I'm doing this reaction, this chloride from this mechanism can take off any hydrogen. So as you start building up the concentration of this, it could take off one of these hydrogens, but it could also take off one of these hydrogens. So if it took off one of those hydrogens, it becomes CH2Cl2. Then as you build up the concentration of this, you can do the same thing, make some chloroform, until it was all halogenated. And so when we work these problems, we're going to limit our discussion to the monochlorinated products. So to draw the products of this reaction, you'll need to replace each type of hydrogen with the respective halogen. So we're going to look at 2-methylbutane. Let's go ahead and draw it out. So any one of these hydrogens on this compound can be replaced with a chlorine. So like one of these hydrogens of the CH3 can be replaced with a chlorine. Now do you see if I replace one of these hydrogens, it's the same thing as replacing one of these hydrogens. So any 6 of these hydrogens would give you the same product. has to know these two methyl groups are attached to the same thing. But this methyl group's attached to something different, so that would be a different product. And you can see if it's different is by naming it. If you replace this one, if I put the CH2Cl here and named it, I would have got the same name as this one. So here's a different hydrogen here. Let's go ahead and number the different ones. So those two hydrogens, all 6 of those hydrogens are equivalent. That one's different, that one's different, and those are different. So I'm going to have 4 different products there. So this is a product from A. So that would be B. That would be D. Four different products there. Due to the relative stability of the reaction intermediate, so going back to the mechanism, the reaction intermediate is an alkyl radical. So the more substituted the radical, the more stable it's going to be, so more likely to form. And so you can actually predict what's going to be your major product that was. So if I look at A, those are primary carbons. B is a tertiary carbon, C is a secondary carbon, D is a primary carbon. And so B is going to form a more stable intermediate, but there's only one of those positions. If I look at this primary position, it's not going to form as stable as an intermediate, but there's so many more of them, you can see a lot of that product as well. So we have these different ratios for chlorine and bromine, where you can actually predict how much of each product that you will have. So for chlorine, for primary, secondary, and tertiary, so if we say primary is 1, we'll see that secondary is 3.5 times more reactive, tertiary is 5 times more reactive than a primary position. Bromine is much more selective in that the secondary position there is 82 times more reactive, tertiary is 1,600 times more reactive. But we can use these selectivity ratios to calculate the percentage or predict what percentage of each of those products that I would have. So that's what this problem is asking about on 10-4. It says, taking the relative reactivities of primary, secondary, and tertiary hydrogen atoms into account, what products would you expect from monochlorination of 2-methylbutane, and what would be the approximate percentage of each product? Don't forget to take into account the number of each kind of hydrogen. So if I look at A is primary, so selectivity ratio of that is 1. But I have to take into account the number of those types of hydrogens. So on A, I have 6 of those hydrogens. So I take 6 times that ratio. If I look at B, B is tertiary, so that's 5. If I only have one of those, if I look at C, it's secondary, so that's 3.5, and I have 2 of those. And then if I look at D, D is also primary, so that's 1, and I have 3 of them, so I multiply it by 3. Now I want to do a percentage. So to do a percentage, I need to add up my total here. Okay. So is that 21, 6 plus 5, 11, 18, 21. So to find my percentage then, I'd say take 6 over 21 times 100. 5 over 21 times 100. 7 over 21 times 100. 3 over 21 times 100. So 29%. 4%, 33%, 14%. On the exam, you can just put this part here, like 7 over 21 times 100, and that'd be fine. You calculate out your ratios. This way is how you predict how much product you have. Let's look at another one. Look at the problem from your notes. It says calculate the product ratio for the chlorination and bromination of 2,3-dimethylbutane. And it says chlorination and bromination. Well, if I look at this one, this is different from the previous one in that in this case, all the methyl groups are equivalent. All the methyl groups are attached to the exact same thing. So just replacing any one of those would give me the same product. And then my 2 CHs are also equivalent, so I have a plane of symmetry here. So now if I calculate the ratio of each one of these, so this group here for A, those are primary. So primary is just 1. And I have 6, 9, 12 of those hydrogens. So I'm going to take 12 times 1. And the selectivity ratio for tertiary is 5. And I have 2 of those positions that are equivalent. I multiply that by 2, I get 10. So I add those up, 22, so 12 divided by 22 times 100, and 10 divided by 22 times 100. Now, if I look at bromination, get the same products. Put my bromine on a different one this time. Because it doesn't matter which one I put it on, because they're all equivalent. Again, just to change it up some, I'll put it on the other one. That's going to be equivalent as if I put it on that one. Now, bromine is much more selective. So, again, if you look at that table I gave for bromine, for primary it was 1. Again, I have 12 of those positions. So I have 12. Here it's a tertiary position. So tertiary position, selectivity ratio there is 1600. And I have 2 of those positions. So I have 12 over 3212 times 100, and 3200 over 3212. So look at the percentages there. So this is what's meant that bromine is much more selective. If you look at chlorine, you do this reaction, it's close to a 50-50 mixture of the 2 products. Because chlorine, even though it's preferred, the intermediate's more stable here, you have so many more of the other position kind of evens it out to where they're close to 50-50. Bromine's much more selective though, and that it's almost 100% bromine at the most substituted position. Look at what's known as allylic bromination now. Alkenes react with N-bromosyconium and NBS to give product substituting bromine for a hydrogen at the allylic position. The allylic position is a position adjacent to the double bond. Position adjacent to the double bond would be there. So, but if you put it at either position, it's going to be the same product. You get 1, 2, 3 bromocyclohexene. Either way. The reaction takes place through a radical mechanism, and allylic radicals are even more stable than tertiary radicals due to stabilization through resonance. So it goes to this radical intermediate. And can be stabilized with that double bond that's adjacent to it. But again, if you substitute at this position of your resonance structure, square up on, you get the same thing. You get the 3-bromocyclohexene. Just to review, N-bromosyconium has that structure, but we'll just write out NBS each time. we'll look at 10-5. Then 10-5 is draw through resonance forms for the cyclohexadienal radical. So there's my cyclohexadienal radical. So I got a double bond adjacent to right here, no double bond here, so I can't move anything from that direction. I can move one of those electrons to form a double bond there, making the radical at the other side of your double bond. And you can do the same thing with this other double bond. Radical goes at that other position. Look at 10-6. So it says a major product of the reaction of methylene cyclohexane with N-bromosuccinimide is 1-bromomethylcyclohexene. Explain. So it says this is the major product. We'd expect just from the reaction of MBS that here's my double bond, here's the position adjacent to it, so that's where my bromine, I'd expect my bromine to go. But it says this one is my major product. And that's because if you draw out your intermediate, you can see it stabilized to resonance. So that radical is spread among two different positions, and so that's why you see that as your major product. This is a more substitute alkene, more stable. So when you do this reaction, not only do you have to look at the adjacent positions and put bromines there, you also have to look at the resonance forms of the intermediates and look at those as possible products as well. So it makes this type of reaction very difficult if you do not have the symmetric alkene like was on the very first one. Let's look at another problem. Let's look at 10-7, one of those. Let's look at B. So here I have two adjacent positions. Through my double bond. two adjacent positions. I can look at my intermediate, draw the intermediate for each of those. Now I can draw the resonance forms for each of those. So I'm just moving my double bond over here, then create the radical here. Move my double bond between those two, make my radical at that position. It's just a single bond. Now, every place I have a radical, a bromine can attach. And so I have 4 possible products there. Now we'll look at some other ways to prepare alkyl halides. So another way is preparing alkyl halides from an alcohol. So when we get to organic 2, we'll also see these reactions again when we talk about reactions of alcohols. So alkyl halides can be prepared by adding HCl, HBr, or HI to an alcohol. So you're just replacing the OH with the X. The reaction works best with tertiary alcohols because this reaction always goes through a carbocation mechanism, a carbocation intermediate, which we're going to look at in the next chapter, that mechanism. So it always goes through this carbocation intermediate, tertiary alcohols or tertiary carbocations are more stable. So primary or secondary alcohols are very converted to alkyl halides using thionyl chloride or phosphorus tribromide. So this one is tertiary. So HCl works better. And this is one of the reactions that we'll actually do in lab. We're actually going to take terpyl alcohol, mix with HCl, and get the terpyl chloride. But if you had a primary alcohol, it's going to form a primary carbocation, which is not very stable, so that using HCl would not work very well. So you use what's known as thionyl chloride, SOCl2. It goes through a different mechanism, so it goes faster. Now, if you want to do the same thing with bromine, again, this one's primary. Instead of SOCl2, it's PBr3. If you had the tertiary, you go into bromine there, you use HBr. So 10.8 is how would you prepare the following alkyl halides with the corresponding alcohols? The very first one, on A, was actually this problem here. You were given the terbial chloride, so you just use the HCl. That's the answer to A of that problem. Okay, so I look at this one. So where I have my bromine, I'll take the bromine off. Put the OH there. Now look at the substitution. And that's secondary alcohol. So it's not tertiary. So PBr3 would work the best. But since it is secondary, I mean, you could use HBr as well, but for like primary, it's going to be much better to use PBr3. Like this one here is primary. So that's primary. And so PBr3 would be what you would want to use. So those are some different ways to make alkyl halides. Now we're going to look at some different reactions that alkyl halides can undergo while looking at an area of organic chemistry known as organometallic chemistry. So it's when you have metals incorporated into your organic compounds. And then chapter 11 we'll look more at reactions that alkyl halides can undergo. So one reaction they can undergo is to make what's known as a Grignard reagent. Just introduction to this concept right now. In Organic 2, we'll look and see what Grignard reagents are really useful for. In a Grignard reaction, start with your alkyl halide. You react that with ether. You get what's known as your Grignard reagent. So these are very nucleophilic. Just remember, anytime you have a metal compound in your compounds, like you have a minus charge on the other thing, so this carbon's like this carbon has a minus charge. Not very stable in the carbon atom. They don't like minus charges. Makes it highly reactive. So very good nucleophile. And so what we'll see in Organic 2 is that this will add to carbonyl compounds. But for now, this is how you make it. The halogen may be removed from the alkyl halide by first converting to the Grignard reagent, followed by addition of water or an acid. So you can do like Mg, make your Grignard reagent, use H2O, and that minus charge there is just going to take a proton from your water, and so you end up with your alkane. So this is a method to make an alkane from your alkyl halide. Like I mentioned though in Organic 2, when you do this reaction, you have to be sure there's no water in solution because you want to use it for other things besides making your alkane. And if there's any water present, it would do this. Let's look at 10-10. So it says how much you replace a halogen substituent by a deuterium atom if you want to prepare a deuterated compound. So remember, deuterium is just an isotope of hydrogen. So hydrogen has one proton, deuterium has a proton and a neutron. It's just represented with B, so you can tell it apart from the different hydrogens. Well, I just saw how I could make my Grignard reagent. So I could add magnesium to it, then make my Grignard reagent. Now my hydrogen that I add is H2O, but instead I use D2O. Instead of adding the hydrogen, it add the deuterium. So D2O is what's known as heavy water. Look at organometallic coupling reactions. These types of reactions are used to add alkyl groups to alkyl halides. The alkyl halide is treated with a lithium diorganocopper compound called a Gilman reagent. The alkyl group in parentheses replaces the halogen in the alkyl halide. We'll look at a few examples here. So this is what's known as your Gilman reagent. Your diorganocopper lithium compound. Diorgano because you have two of them. So in this reaction, you just take alkyl groups in parentheses and replace your halogen. So it's just a CH3, so instead of an iodine, I have a CH3 there. These would just be byproducts there. See where everything goes. So this is your major organic product that you draw, though. Again, have my diorganocopper lithium compound. So what's in parentheses, CH2CH3, that is what replaces my chlorine. The Gilman reagents can themselves be prepared from alkyl halides using lithium followed by copper 1 iodide. So you use 2 molar equivalents of lithium. And you take that compound, 2 molar equivalents of it, and react with copper iodide, and you make your Gilman reagent, which can then react with different alkyl halides. Let's look up problem. Let's look at 10-11. Says, how would you carry out the following transformation using an organocopper coupling reaction? More than one step is required in each case. So this is one of those synthesis types of problems. It'd just be a CH3 there. So if I look at the differences between my starting material and product, methyl group attached to the allylic position. Well, I haven't seen a way to attach an alkyl group just at the allylic position. But what can we attach to the allylic position? Position adjacent to a double bond. Covered it earlier today. A bromine using NBS. Now, since I have the bromine there, now I can use my diorganocopper lithium compound. So what's in parentheses just replaces the bromine. Look at C. So if I look at this one, I've got one pentene. I'm going to make decane from that. So I've got 5 carbons here. I want to go to 10 carbons. Well, I know I can add carbons. I don't have a triple bond here, so I can't do that reaction that we looked at yesterday. Okay. I guess you could make a triple bond from that, add 2 halogens to it, then use a 2NH2, and so you could make it from a triple bond. But this problem specifically states to use a diorganocopper coupling reaction in the process. So if I have 5 carbons here, I'm going to add 5 more to it. 1, 2, 3, 4, 5. So what I would need is a bromine attached to the very end. That way I can attach 5 more carbons to it and get my 10 carbon chain. Now that bromine is attached to the least substituted position of that starting double bond. So how do you attach a bromine to the least substituted position? Remember? HBr peroxides. Another reaction that you may see, I think I have this in the notes. Okay, so here's a Suzuki-Muraro reaction, a coupling reaction of an aromatic or vinyl substitute boronic acid with the aromatic or vinyl substitute organohalide in the presence of a base and a palladium catalyst. So here's an example of your Suzuki reaction. So you have some kind of an aromatic compound or vinyl, so aromatic or vinyl, so you have your boron attached to a double bond. Your alkyl halide is also attached to a double bond, and so this is a way to couple those things together. So here's an example of the Suzuki reaction. So again, aromatic compound boron. Here I have my aromatic halide. So I couple them together, and so this is showing you a synthetic process. There's a few more steps after that to make this compound, this pharmaceutical. The generalized equation for that, though, would be I'm just going to put AR for aromatic. I'll put ARX for my alkyl halide. I'll call it AR prime. So it couples the vinyl or aromatic compounds together. The Suzuki coupling reaction is less general than the diorganol copper reaction because it does not work with alkyl substrates, but it's preferred when possible because it only uses a catalytic amount of metal than a full equivalent because palladium compounds are less toxic than copper compounds. So the last thing in the chapter deals with oxidation and reduction in organic chemistry. So organic oxidation results in the loss of electron density by carbon caused either by bond formation between carbon and a more electronegative atom or by bond breaking between a carbon and a less electronegative atom, usually hydrogen. Conversely, an organic reduction results in a gain of electron density by carbon, caused either by bond formation between carbon and less electronegative atom or bond breaking between carbon and a more electronegative atom. Any reaction that converts a compound from a lower level to a higher oxidation level is called oxidation. Anything that goes from a higher oxidation to a lower level is reduction. So if I look at these compounds, rank the following compounds in order of increasing oxidation level. So which one would have the lowest oxidation level out of those? Yeah, the one without the oxygen. So which would be 2 then? Yeah, the OH. And so this one has the highest oxidation level, the double bond to oxygen. So it'd go 3, 1, 2. This is lowest, this is highest. It says tell whether each of the following reactions is an oxidation or reduction or neither. So is this oxidation or reduction? what's happening to the oxidation level? Is it increasing or decreasing? Decreasing, so that'd make it what? Reduction, yeah. How about here? Is oxidation level increasing or increasing? So that'd be oxidation. So this one would be an example of reduction. This one an example of an oxidation. You may also see some things termed a reduction that do not even involve oxygen. Like if you have a C dope on C and you add hydrogen to that, so if you go from an alkene to an alkane, that is also termed a reduction. So if you decrease the high electron character as well, it's termed a reduction. Because you are, let's go back to the definition up here. Organic reduction results in a gain of electron density by carbon, caused either by bond formation between carbon and less electronegative atom or bond breaking between carbon and more electronegative atom. But we'll learn a lot more about oxidations and reductions in organic too. It's just so like this reaction here, even though we see what it does now, we'll actually go over that reaction in detail until organic too. We've covered this one already. Let's go ahead and look at some of your homework problems.